Welcome back. Now, in this section, we are going to look at the stress and deformation, as I said, and we will first look at the elasticity fundamentals. Elasticity or elastic behavior of solid is entirely a big field. If you look at the entire industry of civil engineering, where you have built big dams and big multi-storied buildings and all different kinds of structures, they essentially depend on linear elasticity, which says that if I am going to design a building which is made out of iron beams, I need to know the load which is going on all these structures, which may have the load of the beam itself, load of the structure itself, or there could be wind load. And as you know, you also define it for the storm loads. As you know, right, if there is a lot of snow, the snow is on the rooftop, and that's adding more and more weight. So, if you want to make sure that the building doesn't fail or collapse, then you have to design it with elasticity in mind to understand at what point the material is going to become inelastic. That means it will stop behaving elastic and there will be failure. So, this whole idea about failure of the material under stress and strain condition. So, as you put stress on the system, there is a strain, that means there is a expansion. So, if you look at this slide, this is a generic surface of a particular blob delta S, and we are creating a particular force which is normal to this delta S. And if you look at the force is creating in particular direction, it could be any arbitrary direction. But if you look at this this is new symbol shows the surface normal. So, you always have a direction of the force, the surface normal, and delta S. So, if you look at the stress, which is defined here by T as delta S goes to 0, is dF over ds. That means the force and ds, obviously you have to take the component of the forces in x, y, and z direction. If you are in a Cartesian coordinate, that is where the differential of delta F over delta S, that means the surface area. So, the force that is acting per square surface area is what you call stress. That is the definition of the stress. So, now if you look at here, this looks like a again cubic box where we are looking at various different stress tensors. And the reason we call it tensor, because it is 3-dimensional property, it has x, y, and z. So, you are looking in this particular box, this is the 3-dimensional model, this is the 2-dimensional model. So, if you look at, I just want to pop up here that there are two things here, and sigma has two components x, y, and x and y. So, normally they are defined by two subscript I and j. In this case, eta, psi and eta, which is showing here, where the first subscript is the direction of the surface normal upon which the stress is acting, and the second one is direction of the stress component. So, this is how you are going to define, and this is the second, this is the 2-dimensional model. If you look at just a surface, this is if you have a cube, then this is the 3-dimensional model of the stress tensor. So, now let us do simple derivations of the properties of an elastic system. So, I am going to now do some stuff on the document camera. Let me make that available to you, and then we are now going to do some simple derivation for the elasticity. So, we will first begin with the understanding of what are these different stress tensors and how we can make sense out of them. So, let me first begin with a 2-dimensional model and then extend it to the 3-dimensional model, because it is always easier to start with the smaller dimensions, so that you can go to the higher dimensions after that. So, this is a plane, they call it plane stress situation. This is a particular element, and so if I put stress, these are called principal stress directions. So, think about this is uniaxial stress. So, if I take a beam here and then stretch it on the two sides, and let us call this, let us say this is we are looking into x and y directions. So, we are going to call this as x direction and this is y direction for now. So, now what happens that we have sigma in y direction. So, this is stress in y direction and this is stress in x direction. But now what happens as you move a particular substance, what you understand is that there is also the stress on the other direction, surface normal direction. So, that are the forces which are caused here, which are shear forces. So, there is a shear force because I am moving the system here, and so as I am moving in the y direction, I have two shear forces opposing each other, and this I can talk about. This is tau, and in this case tau x y, and this becomes tau opposing to that tau y x. Similarly, in this case you can look at another tau because I am stretching in the x direction. Now, there are these forces acting upon shear forces, and that become tau y x, and this becomes tau x y. So, if you look at here, and by symmetry what we are saying is tau x y is equal to tau y x shear forces in both cases. So, if I have to create what are the stress, what is the stress tensor here, you have sigma x, and now you have tau y where surface normal and x, and here you have tau x y and sigma y. So, now you understand how this tensor is being generated in 2 dimension, right. So, now we are going to extend this same model into 3 dimensions and then create a 3-dimensional tensor. So, the 3-dimensional tensor here is going to be a cube. So, now we have to define 3 dimensions here. So, let us look at these 3 axes. So, we are going to say this is x axis, this is y axis, this is z axis. So, if you look at here, and if I now just take the z component, which is a uniaxial, which I am doing here, then I can say this sigma. Now, I have to use 2 sigma z z. Now, there is a component which is in sigma, this is the y direction. So, y z, and this is x direction. So, sigma x z. So, now if you look at all these 3 directions x, y and z, then you come up with a matrix which will be sigma x x, which is the principal direction. And then there are other directions which are surface normal to it in 2 directions. So, sigma we start with x y, sigma x z, and then you can go sigma y x, sigma y y and sigma y z. Then you have sigma z x, sigma z y and sigma z z. So, if you look at these 3, sigma x x, sigma y y, sigma z z, the principal direction of stress, and then you have the cross term which is sigma x y, sigma x z, sigma y x, sigma y z and sigma z x and sigma z y. So, if you look at sigma x y, and so these are 2 connected, sigma x z and z x are connected, they are same, and so these 3 are connected. So, now you understand that these stresses can be manipulated depending on different kind of crystal structure. Now, you can understand how the stress situation will happen. And if you had, I will write one last thing for this situation where you have a, let us say, isotropic solid, then a lot of these things become equal. So, you get a 6 by 6 stress matrix, which is sigma 1 1, sigma 1 2, sigma 3 3, sorry, sigma 2 2 and 3 3. Then you have the cross term sigma 2 3, sigma 1 3 and sigma 1 2. So, this is a vector of stress. Now, you also have elastic constants. So, we are going to put those elastic constants C 1 1, C 1 2, C 1 3, which is coming out of sigma x x, sigma x y and sigma y z. So, then C 1 2, C 2 2 and C 3 3, C 2 3 sorry, and then you have C 1 3, C 2 3 and C 3 3. But other components become 0 because we are looking at the principal directions in an isotropic solid. What remains is 1 2 3, C 4 4, 4 5 6, then 1 2 3 4, C 5 5 0, and then finally you have C 6 6. So, if you look at here, then you have this strain component with eta 1 1, eta 1 2, eta 2 2 and eta 3 3. Then the cross term, and in this case 2, because there are two directions here, which has the strain 2 3, 2 eta 1 3 and 2 eta 1 2. And this is what you need to understand, the 6 by 6 component. So, you will have C 1 1, C 1 2, C 1 3 elastic constants. So, these are elastic constants for isotropic material. What I mean by isotropic is that the property of the material is same everywhere, it is not changing. And so, you have then C 1 2, C 1 3, C 2 1, C 3 1, C 2 3 and C 3 2, and then you have these are the principal, these are the cross terms, and then the shear terms are C 4 4, C 5 5 and C 6 6. Now, let me stop here because we now want to move forward with this formulation and with understanding of the basic elasticity. And we are now going to use this kind of formulation to understand how we are going to calculate different kinds of elastic constants. And that is where it is important to first understand what are isotropic solids. Isotropic solids have same properties all over. So, if you look at if you want to find out how many elastic constants you have to use as it is given on your document camera, what you will find that C 1 1 becomes C 1 C 2 2 and C 2 2 is C 3 3, because the elastic constant is same in all three directions, isotropic solid. Then there is another elastic constant which is the cross term, which is what we are looking at 1 2 2 3 3 1. So, there is one elastic constant there, and then there is shear one C 4 4 is equal to C 5 5 is equal to C 6 6. So, now we have only three elastic constants C 1 1, C 1 2 and C 4 4. So, this is how this whole humongous 6 by 6 matrix come down to only three elastic constant if you have a cubic crystal with the cubic symmetry and isotropic solid. Thank you.